Okay, on today's video, we're going to be talking about theoretical probability or just probability. And first off, let's define probability. Probability is the measure of how likely or the chances that something's going to happen. The set of all possible outcomes is called a sample space. What we mean by that, like if I'm flipping a coin, my sample space for that event would be either a heads or a tail. That's everything that could possibly happen. For equally likely outcomes, such as a coin, we know that heads and tails are both equally likely if we flip a coin. The theoretical probability, or what we think the chances of an event happening, we write as this: the probability, the P stands for probability, the probability that the event E, whatever that event is going to occur, is the ratio. It's the ratio of the number of favorable outcomes to the number of total outcomes. Like if I want to know what's the chances that if I flip a coin, a heads is going to come up, the way we would write that is the probability of heads. And the probability of heads is, again, it's going to be the number of favorable outcomes. And what we mean by favorable outcomes is how many successes, how many different, if we had a coin and we're going to flip it, how many different heads could happen. And there's only one heads on a coin, so the favorable outcomes would be a 1. Uh, the ratio of that to the total number of outcomes. We know that on a coin, there's two total outcomes. There's two things that could happen. So the probability that you get ahead is 1 out of 2. That's what we mean by that. Okay, first off, let's work some problems. Simple events. The probability of just one single event happening. It says a jar contains 32 red marbles and 28 blue marbles. What is the probability that a randomly selected marble is red? So we're looking for, and I'm not going to write this on all of them, but just to get you used to the notation, we're looking for the probability of red. And again, we ask ourselves if we're drawing a red from this jar, how many different reds could we draw? And there's 32 total favorable outcomes. There's 32 red marbles out of, or the ratio of that to the total number of outcomes. We know there's 32 reds that I could draw. There's 28 blues that I could draw. There's 60 total marbles that I could draw from this. So the probability is going to be 32 out of 60, which can be reduced to an 8 and 15 chance. Now we can write probability 3 different ways, and that's the first way, and that's as a fraction. We could also write, if we remember that the fraction bar means divided by, so we can type into our calculator 8 divided by 15. We can write our probability as a decimal, and that's going to be 0.53, and the 3 repeats. Or we can write it, most of the time we see it as percent. So move your decimal over 2 places. That's 53.3 repeating percent. So the chances of drawing a red out of this jar would be a 53.3% chance of pulling the red out. Okay, next problem. It says a letter in the word restoration is randomly selected. What is the probability of selecting a vowel? So probability, oops, the probability that we're going to get a vowel. First off, we count, and that's the number of vowels, which there is an E, an O, an A, an I, an O. So that'd be 1, 2, 3, 4. There's 5 total vowels out of the total number of ways that we could pick a letter, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's a 5 and 11 chance that you choose a vowel from this word. And I believe that's right. Let me double check it. 1, 2, 3, 4, 5. Yeah. Which again, we can turn into a decimal by dividing, but I'm more interested in the percentage. Let's write this as a fraction and percent. So let's do 5 divided by 11. Move the decimal over twice, and you get about a 45.5% chance of this happening. Number 3. A day in the month of January is randomly selected. What is the probability of selecting a prime number? Okay, first off, the probability of getting a prime, if we're selecting a day in the month of January, we know there's 31 total months. I'm going to go ahead and write that down. But of those, how many numbers in the numbers 1 through 31 are prime? And let me just remind you real quick about prime numbers that the number 1 is not prime. It's not prime, it's not composite. But 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. And 31 are all prime. That's the prime numbers between 1 and 31. If you don't remember that prime numbers have only two factors, 1 in itself, so that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of the 31 days are prime numbers. We type in 11 divided by 31. We get that's about a 35.5% chance of choosing a prime number. 2 dice are rolled. What is the probability that the sum of the dice on the next roll is at least 9? Now, this one's a little bit tougher. So we're rolling 2 dice, and what we've got here is there's several different outcomes, and you could set and list them all, and it would take a while. You could roll a 1 and a 1, or a 1 and then a 2, and then a 1 and then a 3, a 1 and then a 4, a 1 5, and a 1 6, or a 2 1 and a 2 2 and a 2 3, and so on and so forth. So there's several different outcomes here. Actually, there's going to be a total of 36 different ways that we could roll this dice. And you could see that because there's going to be 6 ways. What if you roll a 1 first? Or what if you roll a 2 first? Then there's going to be 6 more ways. What if you roll a 3 first? So there's going to be a total of 36 different ways that you can roll this dice. And we'll talk, we actually did that in the previous lesson. That's the counting principle. So let's look at that again. So you're going to roll 2 dice. There's 6 different landings for the first roll. There's 6 different ways to roll the second time. So there's a total of 36 ways this dice can be rolled. Now, at least a 9. Now let's try to do this just to speed this up a little bit. Instead of listing all of them, let's list the ones that are going to be 9 and above. So if I roll a 1 on the first dice, there's no way to get a 9. If I roll a 2, there's no way to get a 9. If I roll a 3 on the first dice, I have to roll a 6 to get a 9 on the second dice. If I roll a 4, a 5, or a 4 and a 6 would give me at least a 9, a total of at least 9. If I roll a 5 on the first dice, I could get a 4, a 5, or a 6 on the second dice, and that would give me values that are at least 9. If I roll a 6, I could roll a 3, a 4, a 5, or another 6 would all give me values that are at least 9. So therefore, there's all the successes. There are 4 plus 3 plus 2 plus 1. I believe that'd be 10. So 10 out of 36 ways you can roll at least a 9 on this dice. If you reduce that, that's a 5 out of 18 chance. If you type that in, 5 out of 18, that gives you about a 27.8% chance of this event happening. Okay, number 5. It says, what is the probability of drawing a heart or a club from a standard deck of cards? And let's talk about how a deck of cards is divided. A deck is divided into 4 suits. First off, the suits are the hearts, the clubs, the diamonds, and the spades are the 4 suits. And each of those suits have the numbers 1 through 10, a jack, queen, and king. So each of those suits have 13 of each of its cards. So there's 13 diamonds, there's 13 spades, there's 13 clubs, and there's 13 of each of them. Well, what we're asked for is what is the probability of drawing a heart or a club from a standard deck? Well, I know that there's 13 hearts and there's 13 clubs, and then there's 13 of the other two as well, which gives you a total of 52 cards in a deck. So I know that 26 are hearts or clubs. Out of the total number of ways to draw from a deck would be 52. If you reduce that down, and that makes sense, half or 50% of the cards are hearts or clubs, and that's the reason that probability works out the way it does. The next problem says there are 8 books lettered A through H on a shelf. If Scott randomly chose 2 books, what is the probability that he chose books A and B? Okay, to work this problem, we're actually going to use something again from our previous section. We're choosing 2 different books. We're choosing from these 8 books 2 books, and let's talk about permutations and combinations again. Making a choice of 2 books. Now, I want you to be careful with something because choosing book A, choosing book A and then book B is the exact same thing as choosing book B and then book A because you've made a choice. In the previous video, again, we talked about permutations versus combinations. This would be actually combinations. The reason I'm working it this way is to save me some time of trying not to have to list all the different ways of choosing 2 books. So all the different possibilities of how I could choose 2 books would be a combinations. I have 8 books to choose from, and I'm going to be choosing 2 of them. And that's going to give me how many total ways there are to choose these books. The way we work that, 2 blanks. There are 8 books to choose from for my first blank, and then 7 books to choose from. Let me scroll this up so I quit doing that. 7 different books to choose from for my second one. However, since it's a combination, I must then divide by 2 factorial, which would be 56 divided by 2, which is 28. So what that tells me is there's 28 different ways that I can choose these books. Well, what about choosing books A and B? Well, that's one of the 28 choices because I could choose A and B or A and C or A and D or A and E and through H, or I could choose B and B and A and B were the same thing. So I could choose B and C or B and D. So if you took and listed all those, there'd be 28 different ways. However, the probability of choosing this is one choice. A and B would be one choice out of those 28. So there is a 1 in 28 chance of choosing books A and B. If you were to change that to a percentage, there is only about a 3.6. There's a 3.6% chance of this actually happening, which is not very likely. Okay, next up we're talking about the complements of events, and the best way that I can describe what a complement is the chances of it raining versus the chances of it not raining. We know that it has to do one or the other. It can't do both, rain and not rain. Those 2 events are what's called complements of each other. And we know that if there is the probability of rain is 50%, and the probability of not raining is 50%. If we know the probability of rain is 70%, then the probability of not raining will be 30%. So that's what a complement is it has to do one or the other. And you could actually have multiple events. Maybe you've got a bag with red, blue, and green marbles in it. The probability of red, the probability of blue, and the probability of green drawing out would be complementary events. Those events complement each other. So let's read a little bit more about this. The complement of an event is the probability of the event not happening. Since the sum of all probabilities in a sample space is 1, or 100%, you put both of them, that's the same thing. The probability of an event not happening is the probability, the little squiggly means not. The probability of an event not happening would be 1 minus the probability of the event happening, or 100% minus the probability. Again, the probability of not rain would be 100% minus the probability that it will rain. So if it's a probability of 70% that it will rain, then 100 minus 70 would be, there's a 30% chance of not rain. So the probability that it will snow is 7 out of 20. What is the probability that it will not snow? So if there's a 7 in 20 chance of snow, then the probability of no snow, there's the That's the notation there. It would be a 13. Pretty much what's left out of the 100%. What's left out of the one whole. So the probability of no snow would be 13 out of 20. Next problem says a month of the year is randomly selected. Let's see if I can scoot that over. A month of the year is randomly selected. What is the probability of getting a month that does not begin with the letter A? So what they're doing here is they're showing you that sometimes it's easier to use a complement than it is to actually find the probability that they're asking for. So let's do this. Let's find the probability that we're going to get a month that starts with A. And let's go through and let's talk about all the months that start with A. You got January, February, March, April, May, June, July, August, September, October, November. So only 2 out of the 12 months start with an A, which is the probability of getting a month that starts with A is 1 out of 6. So what they're asking for is what is the probability that the month does not begin with A? So the probability that a month does not begin with A, we could take this 1 out of 6, subtract it from one whole, and we're going to get the other 5 out of 6, which was 10 out of the 12 months do not start with the letter A. Number 9, if the spinner to the left is spun, find the probability that it lands on a number that is not prime. So again, it might be easier here to find, if it will cooperate, it might be easier to find the probability that we will land on a prime. And use that to find the probability that it's not prime. So here's our spinner. So the number 2, 3, 5, 7, 11, 13, and that's it. Those numbers are my prime. So 1, 2, 3, 4, 5, 6 out of the 16 are prime, which means the probability of not prime would be the other 10 out of 16, or there's a 5 and 8 chance of it landing on a number not prime, and you could change that if you'd like to into a percentage as well. 2 dice are rolled. What is the probability of not getting doubles? Well, what is the probability of getting doubles? Let's do it first. The probability of doubles, again, there's 2 dice being rolled. There's 6 different ways the first dice can land and 6 different ways the second dice can land. That's a total of 36 different ways, 36 different things we could get on this dice. Doubles would be a 1 and a 1, a 2 and a 2, a 3 and a 3, all the way through a 6 and a 6. So there's 6 different doubles out of those 36 rolls. So there is a 1 in 6 chance of rolling a doubles. So the probability of not getting a double would be the other 5 out of 6. Simply subtract that 1 out of 6 from 1 and you get 5 out of 6. Okay, now we're going to be talking about compound events. And the word compound events is just like a compound sentence, which we know a compound sentence is 2 sentences joined with conjunction. This would be 2 different events or multiple events. It could be 2 or more. So the probability of 2 or more simple events occurring. Now we got to be careful with compound events because sometimes something happening might influence something else happening, such as if it's raining, that might influence our probability of carrying an umbrella around. The same thing here, that we've got to realize that some events might depend on other events happening. So if 2 events are independent, that means that those 2 events have no impact on each other. That's kind of like I've got a coin in one hand and I've got a dice in another hand, and what I flip on that first coin has no impact of what I'm going to roll on that dice. Those 2 events are independent of each other. However, the example I gave you earlier about rain outside and the likelihood that somebody's carrying an umbrella, those would be dependent events. That second event, the probability of that happening increases as the first event increases. So here's our formulas, and this is actually the exact same thing that we did for our counting principle in the previous video. If you have 2 events that are independent, when the outcome of one event does not affect the outcome of the other event. Here's all you do. The probability that A will happen and then B will happen, and there's two different events. And all you would do is find the probability that A happens, find the probability that B happens, and simply multiply the two together. The second one, dependent events, when the outcome of one event does affect the outcome of the second event. You do the same thing. You've got the two events. However, you find the probability that A will happen, and then the probability that B considering A, as how I'm going to put this, happens. And then you're going to multiply the two together. So it's very similar, and you'll see that as we work through these examples. Independent events, and they've even labeled it for you out here. These events don't get impacted at all from the first one. A dice is rolled 3 times. What is the probability of getting ones on each roll? So the way that I do this, okay, we want the probability of getting a 1, then getting another 1, then getting another 1. So that's actually 3 different events, and just because I roll a 1 the first time does not mean it's more likely to roll it the second time or the third time. So that's what makes these independent of each other. So there's 3 different events happening. So what I do is I draw 3 blanks. And then I work these one at a time. What is the probability of getting a 1 on my first roll? Well, I know that there's only 1 on the dice, and there's 6 total sides. The probability of rolling a 1 would be 1 in 6, and then forget about that and go on to the second roll. What is the probability of rolling a 1 my second time would be a 1 out of 6 as well. And then my third time, the probability would be another 1 out of 6. Now, to find the answer, the same way you did with the counting principle, you simply multiply these together. 1 times 1 times 1 on top is a 1. 6 times 6 times 6 is a 216. So that's not very likely. There's a 1 in 216 chance, which if you change that to a percentage, is only a 0.5, about a 0.5% chance of that happening, less than a 1% chance, because we know 1 out of 100 would be a 1% chance, but 1 in 216 is a little bit less than a 0.5% chance happening. A coin is tossed, then a day of the week is selected. So we want to know the probability of getting tails and the day of the week starting with the letter T. I'll just put T and T. So what's the probability? There's 2 events happening there. First off, the probability of getting a tails, we know there's only 1 tail on the dice or on the coin out of the 2 sides. So the probability of getting a tail is 1 out of 2. The probability of choosing a day of the week that starts with letter T, we know that there are Tuesday and Thursday are the 2 days of the week that starts with a T out of the 7 days. To find the probability of both of these happen, we simply multiply them together, and we can use our cross canceling there. 2's mark out and leaves me with a 1. That'd be a 1 in 7 chance of this happening. If we change that to a percentage, that's about a 14.3% chance of this event happening. Some more. A bag contains 8 red crayons, 14 purple, 6 yellow, and 4 green. A crayon is selected, replaced, then another is selected. Now, this right here is the most important part of this, is we're going to put it back. So that means the probability of a purple, since I pull a purple out, but I put it back in, that's not going to in any way influence what I draw the second time. The yellow the second time is going to be equally as likely. I've got 2 draws. So I put 2 blanks. The probability of drawing out a purple, well, let's first find out how many total there are. There's 8 and 14 is 22, 28. There's 32 total crayons here. So the probability of drawing out a purple would be a 14 out of 32. The probability of drawing out a yellow, since I put that one back in, is now a 6 out of 32. We can cross cancel. Divide by 2 would be a 7 and a 16. Divide these by 2, there'd be a 3 and a 16. Nothing else cross cancels. That'd be a 21 out of 256 chance. And since nothing else cross canceled, I know that will not reduce. So 21 out of 256 as a percent, that's going to be about an 8.2% chance of that happening. Probability of a green then a red, 2 blanks. Probability of a green would be 4 out of 32, and you could reduce that if you would like to. Then the probability of a red, there are 8 reds, so that'd be an 8 out of 32. And I would reduce those. It's going to make it a little bit easier. 4 out of 32, that's a 1 in 8 chance. 8 out of 32 would be a 1 in 4 chance. Nothing else cross cancels. That's a 1 in 32 chance of that happening. 1 in 32 is about a 3.1, which is very not likely. 3.1% chance of it happening. Probability of 2 purples, again, 2 events. Probability of the first purple would be a 14 out of 32. Followed by the exact same thing. Both of those would reduce. That'd be a 7 and 16 and another 7 and 16, which is a 49 out of 256. And again, I don't have to check to see if that reduces because nothing else cross-canceled. A 49 and 256 chance would be about a 1.9% chance. And finally, the probability of 2 yellows. Again, we do 2 blanks. The probability of, let me go back up there, a yellow was 6 out of 32. The second yellow is also 6 out of 32, and you can reduce these or cross cancel. I'm just going to cross cancel them. That's a 3 and a 16. This is also a 3 and a 16. Nothing else reduces. That'd be a 9 out of 256 chance, which is about a 3.5% chance of that happening. So there's both ways that you can write your answers. Okay, next up, let's talk about dependent events. And you're going to see here the second event actually is changed or influenced by the first event. So using the same examples from above, assume once a crayon is selected, it is not replaced. Now, if you think about it like this, the reason that the first one influences the second one, let's go back up here. What if I draw out 5 crayons and I want to know the probability that all 5 are green? Well, if you replace them, if you draw one out and put it back in, draw one out and put it back in, it's the same. It works out. But since we only have 4 greens, the probability of drawing out a 5th green we know would be impossible unless we replace them. So therefore, that's the reason that the previous draws actually influence the later draws. So here's how we're going to do this. Since they're not replaced, we still have 2 events. The probability that we draw a yellow with my first draw, there were 6 yellows, so it would still be a 6 out of 32, but now we got to be careful because we drew out a yellow and we don't put it back in. So now there are no longer 32 crayons in there. There's only 31 crayons to choose from. So when I drew that yellow out and I didn't put it back in, now the probability of drawing out a red is not out of 32 anymore, but now out of 31. So how many reds are in there? There are 8 reds out of the 31 crayons that are left. Then, so you see it's worked very similar, but it's not much tougher. Cross cancel, the 8 and 32 leaves me with a 1 and a 4. The 4 and the 6 were reduced to a 3 and a 2, which gives me a 3 and a 1 on top. 3 times 1 is a 3, and 2 times 31 is a 62. And since I reduced it all the way, I know I don't have to check to see if that reduces. And a 3 and 62 chance as percentage is going to be about a 4.8% chance of this happening. The probability of a purple then a green. Again, there's 2 choices here. There's 2 things happening. The probability of drawing out a purple, there are 14 purples out of the 32 crayons that are in there to begin with. But again, since we drew out a purple crayon, we know that there's only 31 crayons left. So the probability of now drawing out a green would be there are 4 greens out of those 31. So there's your probability of that happening. Let me zoom in just a little. Cross canceling, the 32 and the 4 reduces to a 1 and an 8. The 14 and 31 don't reduce or cross cancel, but the 14 and the 8 will, and that leaves you with a 7 and a 4. So on top, I'm left with a 7 times a 1, which is a 7. On bottom, I'm left with a 4 times a 31, which is a 124. So there's a 7 in 124 chance of this happening, which is about a 5.6% chance of this event occurring. Probability of 2 reds. Now this is getting a little bit more difficult. 2 reds, you got to be really careful here. There were a total of 8 reds out of the 32 crayons. But be cautious because, again, you drew out a crayon and you did not put it back. So that means there's only 31 crayons left to make your second choice from. However, if you think about it too, you drew out you're drawing out a red, then another red. So since you drew out a red and did not put it back, there's no longer 8 reds left in that bag. But there are now only 7 reds left. So therefore, the first red, there was an 8 in 32 chance. Once you drew it out and did not put it back in, now there's only 7 out of the 31 crayons left that are red. 8 and 32 reduces to a 1 and a 4. 7 and 31 does not reduce. 7 and 4 does not reduce. So therefore, that leaves me with a 7 out of 124 chance, which is actually the exact same answer as the previous problem. So that'd be a 5.6% chance of this happening. And finally, 2 greens. Hopefully we're catching on now. The greens, there were 4 greens out of 32, so this is not going to be very likely. So there's a 4 in 32 chance of the first green being drawn out. There is only 3 greens left after you draw that one out and not replace it out of the 31 crayons that are left. 4 and 32 reduces to a 1 and an 8. 8 and 3 do not reduce, and neither does 31 and 1, so that leaves you with a 3 out of 248 chance, which is not going to be very likely. 3 out of, and again, as I'm typing this in, that means if you were to perform this experiment 248 times, on average, only 3 times would this 2 greens occur. And that's only about a 1.2% chance of the time, or percent of the time, will this event actually happen. Okay, number 21. A card is drawn from a standard deck, not replaced. Again, that's the key right there. That makes these events dependent. The second one depends on the first one. And then another one is drawn. What is the probability? So we're making 2 draws. What's the probability of choosing a heart and then a spade? We know that there is a 1 in 4 chance. Or actually, let's do it like this, just to make it make a little bit more sense. The probability of drawing out a heart. I know that 13 out of the 52 cards is a heart. So I've drawn out a card and I did not replace it. I did not put it back in. So there's no longer 52 cards to choose from, but there is now only 51 cards to choose from. And I do know in my first draw that I drew a heart. So we want to know what now is the probability of drawing out a spade in the second draw. And there are 13 spades left. So there's a 13 and 51 chance of drawing out the second one. And you can multiply those together. We're going to get rather large numbers here. 13 times 13 is 169 out of 52 times 51 is 2,652. Now let me show you another perk of writing this thing as a percentage. I really don't want to try to even reduce that. You can try to cross cancel here and it will. That would be a 1 and 4, or we could have cross canceled. We could have reduced this here. That would be a 1 and 4. But let me show you this. If you're going to a percentage anyway, it really doesn't matter because no matter if you divide it here or if you divide the reduced form, you're going to get the same answer. So 169 out of 2,652 would be a 6.4, about a 6.4% chance of this happening, which is not extremely likely. That again, if it was performed, let me do the reduced form. 1 times 13 is 13. 4 times 51 is 204. There's the fraction reduced down. So if you perform this experiment 204 times, only 13 times out of those 204 do we expect this to happen. Okay, the last problem, number 22. Jack had 4 Snickers bars and 8 Mars bars. He randomly chose a piece of candy, ate it, then chose another. What is the probability that both candy bars were Snickers bars? So he's making 2 choices. So again, we do 2 blanks. He has 4 Snickers bars and 8 Mars bars, which means it's a total of 12 bars to choose from. The probability that he chooses a Snickers bar first, which would be a 4 in 12 chance, and then choosing another Snickers bar. Well, there's only 3 left now to choose from, or to choose the Snickers bars out of 11 candy bars that are left. So it'd be a 4 out of 12 times a 3 out of 11. We can reduce. That's a 1 and 3. 3 and 3 cancels completely. So there is a 1 in 11 chance of this happening. So that is your answer as a fraction. If we change that to a percentage, 1 divided by 11, that's going to be only about a 9.1% chance of this happening.